It's a bit of a paradox, but one of the best ways to make your machine learning model smarter is to actually make its job harder, intentionally. Today, we're going to dig into a really clever technique called dropout, and it's all about learning by forgetting. So let's start with a situation you've probably run into. You train a model, and its accuracy on your training data is, say, 99%. That feels great, right? A total win. But what's actually going on under the hood when a model seems to know all the answers that perfectly? Well, the reality is a little less rosy than you might think. This is a classic problem, and it's called overfitting. Think of it like this. The model stops being a student and becomes a memorizer. It gets so good at the practice test that it doesn't just learn the underlying concepts, it actually starts memorizing the exact questions, including any typos or random noise in the data. So when you give it the real test, new data it's never seen before, it just falls apart. It learned the wrong thing. Okay, so to figure out how we fix this, we need to peek inside the network. The heart of the problem, it turns out, is a kind of codependency that starts to form between the neurons. So picture all the neurons in a network learning together. Over time, they can form these little cliques, these highly specialized partnerships. You might have one neuron that learns to only trust the signal from another specific neuron. This creates these really rigid, fragile pathways through the network. And sure, it works perfectly for the training data they've all memorized, but the second you show it new data that's just a little bit different, that whole brittle chain of logic just shatters. So how do we break up these cliques? How do we stop this codependency? Well, the solution is surprisingly simple, and it's something we can all relate to. Let's imagine our neural network as a project team. Right. Now, if you know that any one of your team members might just not show up for work on a given day, you can't afford to have one star performer who does all the important stuff. Everyone else has to step up. The whole team is forced to become more capable, more versatile, and less reliant on any single person. No one becomes a single point of failure, and that's exactly the idea we're going to apply to our network. So here's how it plays out. At first, the network learns and forms all these connections. Inevitably, some of them become codependent, but then we introduce a little chaos. During training, at every single step, we randomly tell a bunch of neurons to just take a break, sit this one out. The neurons that are left can't rely on their usual partners anymore, so they're forced to learn more general, more robust features all by themselves. And this process, counterintuitively, makes the entire team, the entire network, way stronger. Okay, so that team analogy is a great way to build intuition. But how does this dropping of neurons actually work in practice? Well, the formal name for this technique is dropout regularization, and it has two very distinct modes of operation, one for training and one for testing. The first thing to get is that dropout is a regularization technique. That's its whole purpose in life, to stop overfitting and help the model generalize. And it's pretty blunt about it. During each forward pass of training, it just randomly picks some neurons and sets their output to 0. For that one update, they're completely silent. They contribute nothing. Now, how much chaos do we add? Well, that's something you control with a hyperparameter called the dropout rate. It's just a fraction. A dropout rate of 0.2 means you're randomly dropping 20% of the neurons in a layer. A rate of 0.5 means you're dropping half of them. And as a rule of thumb, for those dense, hidden layers in a network, a value somewhere between 0.2 and 0.5 is a really common place to start. Okay, this next part is maybe the most important technical detail to remember. Dropout only happens during training. When it's game time, when you're actually making predictions on new data, we turn it off. We use the full intact network, with every neuron active. But wait, if more neurons are active now, won't the output be way too large? To fix this, we scale down the outputs of all the neurons at test time. It's a simple trick to make sure the layer's total output stays balanced, kind of like it was during training. All right, so where does this technique actually get used in the real world? Because knowing when and where to apply something is just as important as understanding how it works. Dropout really has its moment to shine in the dense, fully connected layers of a neural network. You know those layers where every neuron is connected to every neuron in the next layer? They have a massive number of parameters, which makes them super prone to overfitting. So if you look at a lot of classic computer vision models, you'll almost always see a dropout layer sitting right after a big, fully connected layer. It's a bit less common to use it directly on convolutional layers, mainly because they already have some built-in regularization properties. And it's also worth remembering that dropout isn't a silver bullet. It's just one tool in a bigger regularization toolbox. You've got other things like L1 and L2 regularization, which basically penalize the model for having excessively large weights, and early stopping, which is as simple as it sounds. You just stop training the moment your model's performance on a validation set starts to get worse. So, is there a catch? Well, kind of. There's a trade-off. Because the network is learning in this noisy, challenging environment, training with Dropout almost always takes longer. But that extra training time is usually a price worth paying for a final model that is way more robust and performs much better on data it's never seen. So if we were to boil this all down to one sentence, it would be this. Dropout prevents overfitting by forcing a neural network to learn redundant representations, making it much harder for the model to cheat by relying on any single pathway.
And the key takeaway? To build truly robust systems, sometimes what you need isn't more control. Sometimes you need to introduce a little bit of chaos.